So a reaction where heat is released to the surroundings. How do you know if you've got an exothermic reaction? If you've carried out an exothermic reaction, how do you know it's exothermic? Because you can't really see heat being released. So careful when you say loses heat. You're talking about temperature. That's the thing you can measure. You can't really measure heat. It's temperature that you're measuring. So you get a temperature increase for exothermic. So whenever you have a reaction where the temperature gets hotter, it's an exothermic reaction. And the overall energy change is negative. So energy change, let me rub this out so I don't. Energy change, which we use the symbol delta H for, you might have seen this, delta H. So that just means energy change, the total energy change in the reaction. Then the value for this is a negative value. So if you have a negative delta H value, it means you have an exothermic reaction. Then, we got endothermic. Reaction where heat is taken in from the surroundings. So I'm not going to write the whole thing. Might as well, because you guys are going to screenshot it later, aren't you? So a reaction where heat is taken in, so that's released, taken in from the surroundings. And you know it is endothermic if the temperature decreases. And also, your delta H value is positive. Temperature of what decreases? The temperature of the reactants or products. So if you carry out your reaction in a beaker and you put a thermometer in, the temperature reading will go down, or the temperature will go up if it's exothermic. Right? Another important thing here is the reaction profile diagrams. So the reaction profile diagrams, what do they show? Activation energy is on it, yeah, but what does the whole graph, what is it supposed to show? Yeah, you guys are basically, you're telling me what's on it. Okay, so what it does is it shows how energy changes throughout the reaction. So shows how energy changes throughout the reaction. So does it increase? Does it decrease? How does it increase? Does it just go straight down or not? All right. But what you guys said were right. You were basically telling me the labels, most of you guys who commented. So let's draw a rough sketch of each one. So you got one for exothermic reaction, and you got 1 for endothermic reactions. So we'll start off with exo. On your axes, what you usually have on the y-axis, you have energy or enthalpy, and on the x-axis, you have the progress of the reaction. So what that means is basically the different stages of the reaction. So the starting point, the middle point, the finishing point. It's not really time. It's not the same as time. Time would be every second. This isn't every second. It can change. Some reactions happen really fast, some reactions really slowly. It's just the different stages of the reaction. That's what progress means. So how does it look like for an exothermic reaction? How would I draw it? So let's talk about the energies of the reactants and the products. Reactants high, products low. Yeah, because remember, energy change is negative. Heat is being released to the surroundings. When I say heat, I mean heat energy. Heat energy is released. So if heat energy is released, that means the energy of your reactants is what you start off with, is going to be high, and then it's going to lose energy to the surroundings, and it's going to end up low. So it's going to go from this stage to that stage. So this here would be your reactants. This here would be the products energy because it's lower. And in the middle, I'm sure you guys would have seen at some point, it doesn't go straight down. There's a bit of a hump. It goes up and then it goes down like that. I'm hoping this looks familiar. I'm hoping you guys have seen it somewhere before. And what you need to be able to do is to label activation energy and the overall energy change. So where do we label both of those? Activation energy and overall energy change. Activation's at the peak. Yes, it is at the peak. So let me zoom into that. So what you want to do for activation energy, you want to go from the reactants to the highest point on the graph. It's always from the reactants to the highest point. So this distance here is activation energy. Activation energy is basically the minimum amount of energy needed for a reaction. Let's write this here. Minimum energy needed for a reaction to start. So basically the reaction needs to go over this hump. It needs to go up. And then after that, it naturally happens. Then you've got energy change. Energy change is basically the overall energy change from the reactants to the products. So I'm going to draw a dotted line here, which is meant to represent the products. So if you get asked to label that, you draw an arrow downwards like that. I'm going to just write delta H because we've got up there what it means, right? Energy change is delta H. All right. So for endothermic, it's pretty much the opposite. There's some things that you need to notice. So reactants start low. Remember, it's where heat is taken in, heat energy is taken in from the surroundings. So it takes it in from the surroundings and the overall energy goes up. And again, there's a hump. It needs to go up at activation energy and then come back down like that. So when this happens, so reactants, products, your activation energy, tell me where you think the activation energy is here. Because it's not what some people make a mistake here. So, okay, so some people are making the mistake. It's not peak to products, okay? So that's a common mistake. It's not this. Loads of people think it's this. That's not right. It's actually from the reactants to the peak. It's always the reactants to the peak. The difference is here the reactants are much higher, so it looks small, but for endothermic, you need to go all the way from the bottom to the top. That's a common mistake people make. So what's happened there? So you need to go all the way from the bottom, all the way to the top. That there is the activation energy. So don't get caught out. Which makes sense because in endothermic reactions, you need a lot of heat to start the reaction. You usually need to use a Bunsen burner to start it. So that's why there's such a big activation energy there that you need to overcome. Then you've got your energy change. Energy change is pretty much the same. It's from reactants to products. It's just the arrow this time is upwards rather than downwards because it's a positive change. So that's your delta H. Okay. Right. So let's get into some questions here. I'll go back to that. I'll keep going back to that. You guys can screenshot. This question is about oxygen. Hydrogen reacts with oxygen. Here we have the reaction. Figure 2 shows the relative energy changes. So it's basically drawn an example of a reaction profile diagram. Label the activation energy. So I'm hoping everyone knows it's going to be not a downwards arrow. It's an upwards arrow, guys. For activation energy is upwards. Activation energy is always upwards. The only thing that can be downwards is delta H. Delta H can be upwards and downwards, but activation energy always points upwards because it's the energy you need to put in to start the reaction. So labeling it, dotted line, arrow like that. What's delta? Delta means changing. So if you see triangle, it means changing. So delta H means changing. This means energy or enthalpy. I think you see in physics as well. You see delta T or delta theta, change in temperature. These mean, yeah. So if you see triangle in science, it usually means changing. Overall energy change would be downwards. Yeah, it's not asking us for that, but the overall energy change would be downwards. It would look like that because it's exothermic. So this is exothermic. You're going from a high level to a low level. All right, next one. Determine the overall energy change. Okay, so now it's asking for it, but it's not asking you to label it. It's asking you to find the value. Determine the overall energy change for the reaction between hydrogen and oxygen shown in this question. Use figure 2. So using this, guys, it's asking you to work out, let me zoom in. It's asking you to work out the overall energy change, the actual value. So what would you do to do that? Yeah, so you look, so the answer's, yeah, good. So the answer's not 800. 800 is the value of the reactants. Then you look at the value of the products. So you get a ruler. I do have a ruler, but I'm going to do it without a ruler. Like that, okay? Read it off. So here we've got, like you guys are saying, 800, and then down here we've got 300. So the overall energy change is from here to here. So it would be 500 or minus 500. They accept both. Technically it's minus 500 because it's exothermic. So to show your marks, show your working out, you do 800 minus 300, which gives an answer of 500 kilojoules. But yeah, like I said, it's negative. It should be minus, but you get the marks here. How can you tell if it's exo or endo? You always look at the flat parts. So this part, let me get a different color. Compare this with this. That is not a great color to be using. So if the first one, the reactants are higher than the products, it's exo. If the reactants are lower than the products, it's endo. From looking at the equation, how can you tell if it's exo or endo? You can't. They'll have to tell you. You can't look at the equation and tell. Sometimes they might give you a delta H value on the side. They might say the delta H is equal to like minus 28 or something. If they do that, then the minus tells you it's exothermic. But just from the equation, you cannot tell. They'll have to give you something else. And here they've given us this graph to tell us whether it's exo or endo. What does delta H mean? Delta H means change in energy. So overall energy change in the reaction. Okay, all right, let's move on. This is a bonding question. So let me just go through this real quick. We've got, if you're not sure on this, then I've got this on YouTube. We did a bonding live, so you can watch that if you're not sure. But this is the method that I teach on that. So you write the outer electron. So you got 6 crosses, 6 dots. And what you want to do is from this side, you've got 6. You need 8 to get a full outer shell. So you borrow 2 from here. So let's take these 2. If you're borrowing it or sharing it, you put it in the middle. On this side, you've also got 6 electrons. To get a full outer shell, again, you need 2. So let's take these 2 and put it in the middle. So we've used 4 so far, 2 of each. And then whatever you're left with, put it on the outside. So 1, 2, 3, 4. So that's 1, 2, 3, 4. And then we got 1, 2, 3, 4 dots as well. 1, 2, 3, 4. Okay. I went quite fast because we've done this already, but if you do want to go onto the page, so Flash Revision Lab on YouTube, we've got one here, bonding. So we went through all of this and I go through it much slower. So take a look at that if you want to practice covalent bonding structures. All right, moving on. Okay, so here we have a bond energy calculation. So before we start this, let's add to our notes. What's the working out that you usually do for bond energy calculations? Yeah, bonds broken minus bonds made. All right. So the reason you do these bond energy calculations is to find the energy change. So to find delta H, that's your aim usually, is to find delta H. And the way you do it is you work out the bonds broken and you minus it from the bonds formed. I'll show you how to do it in a second. Another way to think about this is just do bonds in reactant the bonds in the reactants minus the bonds in the products. Okay, so remember that we're going to use that. So back to our question. So what we've been given here are different bonds and the bond energy. So what's bond energy mean? It's basically the amount of energy you need to break this type of bond, this type of bond, and this type of bond. So amount of energy needed to break a bond. So for example, to break a bond between H and H, you need 436 kilojoules. And it's asking us to calculate the energy change. So like I said before, it's asking us to calculate delta H. So how do we do that? We do what I said earlier. You do bonds of reactants or bonds broken minus bonds formed. Okay, so bonds of the reactant minus, I'll say bonds of products. So our reactants, we've got 2 H2s, 1 oxygen, and our products, these are reactants, our products, we've got 2 H2Os. Okay, so we've basically got 2 H2s, so that's going to be H, that's 1 H2, that's another H2, plus oxygen. Oxygen looks like this, it's a double bond, they've just told us that. All of this added together gives us our bonds of the reactants. Then for bonds of products, we've got water. They've given us the structure of water as well, but there's 2 of them. So H2O, H2O. These are all the bonds that we're dealing with. So we're doing all of this minus all of this. So for our calculation, we know 1 H bond is 436. We want 2 HH bonds. So you do 436 times by 2 because we need to break this bond, we need to break this bond. Then we've got O double bond. We've got the value of O double bond here as 498 because we need to break this bond. All of this is our bonds broken. Then we move on to our product side. Okay, so here we've got OH bonds. Can you guys see that? We've got OH bond, OH bond, OH bond, OH bond. How many OH bonds do we have here? 4, yeah. So don't make the mistake of thinking there's 2 because each waters have 2 OH bonds. See that? 1, 2, 3, 4 OH bonds. So we actually need to do 4 times OH bond is 464. So that's our bonds made. So you do all of that minus all of that. Anyone got a calculator? Can you work it out? Not minus 486. Oh, I think it is actually. Yeah, it is minus 486, sorry. Minus 486, well done. Excellent. All right, moving on. Let me know if you got any questions about this one. Next one asks to draw a energy profile diagram for this reaction. So we've just worked out it's minus 486. So that means the products is going to be higher or lower? No, it's not going to be higher. It's going to be lower. It's exothermic. Remember, for exothermic, guys, exothermic, it goes from high to low. So your products would actually be lower down like this. So that means our curve is going to go like that. And then we need to label our activation energy here. And our energy change is minus 486. It's not asking us to label that, but if we were to label it, let me just add it on. If we were to label it, minus 486 would be this value here. Just in case they ask you this year to label it, it'll be over there. All right, let's move on. Right, so we got another one now. This question is about a reaction between ethene and bromine. Complete the reaction profile diagram. So they've told us the reactant's higher than the product, so that makes it exothermic. So we need to draw the hump like that. Label activation energy and delta H as normal. Just like before, this is like a repeat question. So I'll go through it quickly. And the energy change is over here. Okay, here's a slightly different type of question. When ethene reacts with bromine, energy is required to break covalent bonds. Explain how covalent bonds hold two atoms together. This is a bit of a bonding question as well. How would you do that for 2 marks? What would you say? Sharing of electrons between electrostatic forces of attraction. Not intermolecular forces. No, electrostatic attraction was actually right. Yes, Rebecca got it right. So let me explain. Yeah, we use this to explain. So you see, when you've got covalent bonds, what do you have here? You've got a nucleus here. You've got a nucleus here. What are the charges of nucleus? Of a nucleus, what's the charge? It's positive, isn't it? Because a nucleus is made up of protons and neutrons. Protons are positive, neutrons are neutral. So protons are, nuclei are always positively charged. Then in the middle, we've got these electrons being shared. These electrons are negatively charged. So what's holding this whole structure together is the nucleus here, both of them are attracted to these shared electrons in the middle, because positive and negative are attracted to each other. It's like magnets. If you have a north pole and a south pole, they're attracted. So the positive nucleus is attracted to the shared pair of electrons in the middle. And we call that electrostatic forces. So whenever you have something positive attracted to something negative, we call that electrostatic attraction. Okay, so that would be the answer to that. Explain how covalent bond holds. Metallic bonding, we've got that in the YouTube video. So take a look at that. We talk about all the types of bonding in that. So for this one, we'll say 1 mark, electrostatic attraction between shared pair of electrons and nuclei of the bonded atoms, we'll say. Okay. Right, so we've got another calculation here, a bond energy calculation. This one's slightly different because they've given us these bonds, but they've also given us the delta H this time. Right, so something else we need to do. Remember what we said. We said delta H is equal to bonds of reactants minus bonds of products. Right, so what we can do is write down an expression for what we've got here. So we've got our reactants here. So how many H bonds do we have here? We've got 1, 2, 3, 4 CH bonds. So you'll do 4 times 412. But you also have a double bond in the middle. And we know the double bond is 612. So you do 4 times 412 plus 612. That covers this molecule. Plus Br to Br. We don't have Br to Br because Br to Br is what we're trying to find out. That's our X, for example. That's what we're trying to find out. That minus, so all of this minus everything here. So how many CH bonds do we have? We've got 1, 2, 3, 4 CH bonds. So 4 times 412 plus we've got a CC bond here. This time is a single CC bond. So we use this value, 348. Plus, we now got 2 CBr bonds, which is 276. Okay, that minus that equals, so the bonds of reactant minus bonds of products equals our delta H. And our delta H this time is different to before. It's given to us as minus 95. So all of that's equal to minus 95. So can you guys try and work that out? Let me rewrite this down here. So I'll say it again. So 4 times 412, because there's 4 CH bonds here, plus 612, because there's 1 C double bond here in the middle, plus X, because this is what we're trying to find out. We don't get given that in our table. So we'll call that X. All of this minus, there's 4 CH bonds, 4 times 412, plus one CC bond, which is 348, plus two CBr bonds, which is 276. And all of that should equal minus 95. So you need to rearrange all of this to try and get X as the subject. So first of all, tell me what these two brackets are. Anyone worked out what these two brackets are? Okay, everyone's getting different answers. So 4 times 412 plus 612. So 2260. Yeah, I think some of you got that. Yep. So we got 2260. Well done, guys. And then here we got 4 times 412 plus 348 plus 276, which is 2272. So this plus X minus this is equal to 227 is equal to minus 95. So then you need to rearrange this to make X the subject. And what does that give? $276 times by 2. Sorry, this should be times 2, guys. Yep, sorry. There should be 276 should be times 2 because there's 2 of them. Thank you for that. Thank you for pointing that out. So we need to change this. So let's do that again. 4 times 412 plus 348 plus 276 times 2. So that's going to be 2548. So that changes this to 2548 minus 95 plus 2548. And that gives an answer of... Yeah, it was a silly mistake. I said it, but I forgot to write it down. 193. Yeah, so you do minus 95 plus 2548 minus 2260. And that gives 193 kilojoules per mole. Well done, guys. And thank you for whoever pointed that out. Any questions on this? I think this would be as hard as it would get with a bond energy calculation. One where you need to work out the bond rather than the delta H. Okay, good. Let's move on. Right, this one is Edexcel, but you can see it's very similar style question. So it's literally asking us to draw an exothermic and label the reaction profile diagram, identify the activation energy. So literally the same thing. So remember, exothermic high to low. We got the hump. Make the hump go all the way to the bottom. Should label the reactants and products, and then activation energy. Is there. What does it's going to finish soon, probably 5-10 minutes, guys. Yeah, they all seem to be exothermic. That's I wonder, you might get endothermic one this year. All right, another bond calculation here. Calculate the energy change. Right, so H2 plus Cl2 goes to 2HCl. So this time they haven't given the bonds in the actual equation. So maybe I can do that here. So H2 plus Cl2, which is Cl to Cl bond, goes to form HCl, HCl, two HCls. All right, so we got one HH bond. So that's going to be 436. One Cl-Cl bond, which is 243. And then we've got two HCl bonds. So we do 2 times 432. All of this is our bonds broken. All of this is our bonds formed. So we need to minus all of that. And that gives, anyone got the answer? The small 2, no. So the small 2 is taken care of in the table. Small 2 basically means there's 2 H's, but there's only one bond in the middle. In these calculations, you're only worried about the bonds in the middle. So one bond between the 2 H's, one bond between the 2 Cl's, and then you got one bond each here. So in these calculations, yes, only the big numbers are important. It depends on what structure you have as well. If you're confused, just draw it out like this, and then literally one number for every bond you break. So 1, 1, 1, you break it. Even if you have a double bond, count that as one bond. You know, earlier we had a O double bond. Count that as one bond. That's one number. So yeah, good. Getting the right answer. Minus 185 kilojoules per mole. I teach A-level, but I don't do lives on A-level. Sorry. Right, we've got an experiment now. So this is the last question. So student investigate the temperature change when 10 grams of ammonium nitrate was added to 100 centimeters cubed of water. They measured the temperature, added 10 grams of ammonium nitrate, stirred once, and measured the temperature every minute for 7 minutes. What's the dependent variable? So in this experiment, what is the dependent variable? It's not asking what does dependent variable mean, it is asking what is the dependent variable. Yes, it's temperature. So the difference between dependent and independent, let's write that down in our notes. Dependent is what you measure. So what's changing? What's independent? Independent, yeah, is what you're changing. Or what you're, yeah. What you are changing. And you can also have control variables. What's a control variable? Where you're keeping the same, yeah. Yeah, so let's look at this. Let's look at the other variables as well in this. So it's only asking us for dependent, but what would be the independent variable here? Yeah, the mass. So the mass of the ammonium nitrate, you can change that. You've chosen to put 10 grams for this, but you can change that. What is the control variable? There's loads. Control variable, you can think of other things. Not same beaker. Same starting temperature. Yep. You want to keep that the same. So room temperature, same. Make sure that it's at the same temperature at the start. Yep. Good. All right. Give 3 improvements. What can we improve about this reaction here? Yeah, digital thermometer. Good. That's one thing we could do. Measure the starting temperature. We assume that they are measuring the starting temperature every minute. So they'll start at 0 minutes and every minute they'll keep measuring. So I think they are doing that. Stir. They are stirring, but what's the problem with the stirring? You can't just say stir because they've said that they are stirring. Insulate. Yep, good. Insulation. So instead of using glass, what's a good material? What's a common thing that you use in experiments like this instead of glass? Yeah. Polystyrene cup. So use a polystyrene cup with a lid maybe. These could be 2 separate points actually. Polystyrene cup, add a lid, that could be one. There's a few other things you could say. Repeat the experiment and calculate a mean. Yeah, some of you guys said that, that's fine. Why do you want to insulate it? Because, think about it, you're trying to find out the temperature change of the reaction. If you don't insulate it, some of this heat is going to go to the surroundings. And if it goes to the surroundings, it's not going to the thermometer. So the temperature you're measuring is going to be slightly less because some of this heat's escaped. You want to keep all the heat in so you get an accurate value of temperature. It's like if you're weighing the mass of something, you want to keep it all on the mass balance. You don't want parts of it like flying off, otherwise the mass is going to be wrong, isn't it? Or like if you're weighing yourself, if you put like a really heavy jacket on, it's not going to be accurate. It's like that basically. Insulation, yeah, this comes under insulation, so that's fine as well. Here's the notes you guys can screenshot.